It's 6 o'clock, so why don't we get cracking? I hope everyone's enjoyed their semester break. How did you all go with project 2? Does anyone have any thoughts or comments they want to share before we start? I guess it's all a distant memory now, I suppose, which is probably a good thing for a lot of people. So project 1's great. We're going to cover project 2 in this unit and the next unit. So I'm going to give 3 hours of lectures here on projects on unit 6, and then continue with another 3 hours on unit 7. So it's all these units here. This one's all about Monte Carlo and discrete event simulation, and the next one's about working with data. And Yoni's going to finish up Unit 8, presenting machine learning. So the kind of, and you probably can't really see here, the kind of stuff that we're covering in these units is what I do in my day job at a company called Alara. So we run a lot of simulation and optimization and machine learning software for businesses to help optimize businesses so they can, and other things, potentially things like hospitals or other things, to try and optimize their outcomes. So for a very capitalistic business, it's probably simply profit. But you might have other measures for a hospital or something, and you might have a bunch of decisions you want to make, rostering, price setting, or many different kinds of spaces of decisions you make in the business. And sometimes it's easy to kind of guess what a good answer is for something to do, a process or a decision you need to make. And other times it can be very complex. You have to use gut feeling to figure out, like, oh, on Tuesdays I need more people or something. So we use a lot of mathematics to kind of learn. Well, so first we kind of create a model of your business, and we kind of use previous data to kind of model your business using machine learning, which we'll cover at the end. And we use that to predict the future, and we can optimize future outcomes based on decisions you make now, using sort of mathematical simulations and Monte Carlo and things like that. So it's sort of very exciting being here to talk about some of these things. So just to go back to the course topic. So what we're going to do is we're going to cover some material for simulation, discrete event simulation, and randomness. I'll cover randomness today. We'll talk about simulation next Monday. And you've got project 2 coming up. Now, you can go away after today and start on project 2. There is some content in there which won't depend on what we learn on Monday. But there's also some content in there which will depend on the material on Monday. Okay. But as you probably know from project 1, you probably want to get ahead of these things, start taking a look, especially if you've kind of read through the project before Monday, you'll kind of know what to get out of the lecture, and vice versa. Once you've read the lecture, you'll understand the project. We'll be here for, we've got tutorials. Your practicals are on to support the project. And we've also got the Thursday help sessions with Yoni and I. Just dial in to Zoom if you have some specific questions, and we'll give you a hand. Yeah. So we'll get cracking. Oh yeah, project 2 is here. I did hear you might need to refresh your browser. So you press this little button here, maybe with control, to get to the latest version of this. But yeah, there's various aspects to this. But yeah, take a look through. And here are the lecture notes. Yeah, I'll just make sure I got the latest version. Sweet. Okay. So Unit 6 is all about Monte Carlo and discrete event simulation. Now, these might be terms you heard of, or they might not be terms you heard of. But we're going to do something quite different to sort of computer algebra, okay? So Monte Carlo is all about randomness, which is sort of the extreme opposite of trying to find, the integer roots of a polynomial or something like this. And we're going to move into simulation. Now, I'll cover more on simulation on Monday, okay? But generally, if you're trying to simulate a system, a physical system, a sort of more abstract system, like a coronavirus spreading or something like modeling, it's going to involve a bit of randomness, okay? Most processes, they aren't fully deterministic. Or, even if you believe the universe is fully deterministic, there's no way to actually have enough information to 100% predict the future. So we have to sort of, we want to think about and talk about and model and calculate and simulate systems with randomness in them. Okay, and so we'll learn how to do that. Monte Carlo is an interesting word. So it's a city in Monaco where they have a lot of casinos, and Monte Carlo is a famous casino known for gambling. So it was used in the Manhattan Project in World War II and around that time when they were developing nuclear weapons, and they were trying to figure out how to make better nuclear weapons. And they just built computers like the ENIAC machine, and they kind of realized that for all sorts of different simulations, some of the researchers there, Stan Ullum, John von Neumann, and Nicholas Metropolis, amongst others, realized you could use computers to kind of write out a bunch of do all these things, random things, to come up with an answer for something which is normally deterministic. Okay, so previously it's well known that, like, let's say you wanted to simulate a random process like a coin toss, right? You could like physically toss the coin 100 times and do the statistics, right? That's where statistics comes from. Or if you had a more complicated system, which has a series of steps, like a Markov chain or something, you could obviously take it step at a time and use some randomness and then take an ensemble of simulations with different realizations or trajectories with randomness. But what these guys realized is that there's actually a much wider range of problems that you can solve using randomness. So you could solve deterministic problems. In sort of the degenerate case, you might want to know the mean outcome, and you can simulate that, which is like a deterministic number, right? And you can simulate a bunch of trajectories to get the mean. But like you can get much more further away from the obvious there. You can do optimization with simulated annealing. You can use quantum Monte Carlo to simulate quantum wave functions with imaginary and negative components and things like this. Things that don't seem quite obvious at first. So discrete event simulation is a type of Monte Carlo method. Okay, so there's many types of Monte Carlo, as I mentioned. I've personally used like simulated annealing, quantum Monte Carlo, things like this. Solving stochastic partial differential equations. We're going to do something which is probably a little bit simpler to imagine, which is a system which includes a series of discrete events. I'll leave that abstract for a second, but each event might have some randomness to it, like when it happens or what exactly occurs might be a little bit random. So some examples of that, if you're into physics, discrete events, normally physics is all about like integrals and things like that, but discrete events might be like when two things collide, there's an impulse at an instant in time, right? So discrete event means at an instant in time. But in finance, you might think of a transaction where I give you some money and your bank balance goes up and my bank balance goes down at a particular instant. That would be an event. Or it could be a more abstract event, like someone turns up at the shop, someone broke a leg and went to the hospital, someone got infected with coronavirus, something like that. Okay. But an event is something that has sort of a point in time. So we're going to actually go through the process of building an entire, not just describe discrete events and do some simulation. We're actually going to come up with an engine that would let you sort of simulate whatever you want in Julia. Okay, so we'll have this sort of framework, basic framework where you have these basic events. Like I said, I leave that quite abstract. All they have is a time, and they can do whatever, and you'll use that to program your responses in project 2. We'll go through next lecture on Monday what that is, what that looks like. And in your practicals, you'll be going through that with your tutors as well. Okay, going through exercises with that. So you'll have plenty of familiarity with these things so that you can attack project 2. But before that, we're really going to go in a bit deeper into how to do randomness on computers, okay? So we'll do a little bit of an introduction to this. We'll talk about how to go from, say, generating some random bits on a computer to generating a more complicated distribution, like a Gaussian distribution, right? And then we'll just mention a few things you can do. Just a little overview, just a flavoring of what you can do with the randomness before heading into our discrete event simulation. Okay. We'll be using some data structures to help us in that. So we'll have some practice programming with this heap data structure and generic types and things like that in Julia. So you'll have a little bit more, you hopefully be a little bit more comfortable with how to model data and data structures in Julia and to use them yourself. And sort of more pragmatically, I think up till now you've been given a very strong framework with files to edit and things in the course. So we'll be looking at like how do you structure from scratch like a larger program in Julia? How do you break it into different files and modules and stuff like that? And we'll touch on a little bit how to benchmark and optimize some code in Julia, okay? Because this is an interesting point. And there's something that comes up at work, it comes up in the research I've done in the past. With Monte Carlo, the faster your code runs, the more realizations or trajectories or simulations you can run that will end up with a different random result. And if the answer you're looking for is a statistical answer, right, the error in the statistics will decrease if you're doing more and more simulations, okay? So this is definitely a field where you have faster code or more computers, you can get a better answer just by default, by just doing more, right? Averaging over more results. Okay. Yeah, so that's sort of what one of the themes I sort of bring to the courses here. We're really trying to, get you to do some quite interesting things, and also get you how to do it, how to do it fast, right? So hopefully it'll be pretty easy to take this discrete event simulation engine and run a simulation and have it be super fast. All right. Are there any questions before we kind of move on? Do you want to pose me anything? Or... Okay. That's good. That's good. So an interesting thing that we're not really going to talk about is truly random number generators, okay? So we could sit here and flip coins, and hopefully that's pretty random. We could come up with bits. Your Intel CPU or whatever on your computer, I believe it has a component instruction you can call where the CPU will use the kind of thermal randomness. So imagine you had some transistors and they were kind of like finely balanced. The thermal fluctuations could move a few electrons, to the left or to the right, and the CPU can kind of measure those voltages and kind of like turn those kind of random fluctuations into some random bits for you somehow. And even if you don't believe that's good enough, let's say you're worried about the CIA or something's hacked your CPU or something. If you're really extremely paranoid, you can even buy hardware which is based on quantum superpositions. You use some a quantum device to create a superposition or some entanglement or something, and you measure it, you project it down into one of the basis states, and basically you have this kind of like provably random kind of result, right? Well, I mean, theoretically, you should end up with like macroscopic entanglement or something, but it's a very, very robust way of creating some randomness that other people can't sort of predict, which might be useful for cryptography or something. Yeah, sometimes it's very important that no one knows your secrets. So yeah, it's interesting. So people yeah, this was probably more of a joke when I was an undergraduate sitting where you guys are, but yeah, during my postdocs in Spain and that, like I came across people actually selling these devices to like Swiss banks and stuff like that want to do like quantum cryptography and all sorts of different kinds of stuff like this. Yeah. So your computer won't really do these things. That entropy thing I said in the Intel chips too slow. It just makes a few bits here and there, enough to say initialize your computer when it turns on or something. What we want to do is something probably a bit simpler and a lot faster, certainly, which is to use this function called rand and Julia. So let's just look at what this thing is for a minute. If I just go rand and Julia, this is just a nice little function, and it gives me a number between 0 and 1. Okay, floating point number. Now, if I don't want float 64, I could tell it to give me a float 32. Oh, my keyboard's broken. Sorry. I could tell it to give me, I don't know, like a uint 8. And it will give me one of those. I can tell it to give me any number between 1 and 10, and it will do that. So it's quite a flexible function. Okay. So let's look at how it would possibly work. Okay. So in fact, how is it random, right? Julia is a sort of deterministic programming language. So how is this working? And furthermore, how are we going to use this for our scientific computations? Yeah. So the random numbers we generate are what we call pseudo-random. As I said, they're kind of been generated deterministically through maths. So generally, if you think about, you have some deterministic mathematical process, right? It comes in the form of a function, a mathematical function, right? And it's a computer, so it's going to be a function from some bits to some other bits, right? In this case, we're talking about a random process, so it has kind of some hidden state, which are represented with S here, which sort of represents the state of the random number generator, okay? And what we do is using the state of the random number generator, we can spit out some random bits or some random numbers, and the state of the random generator will change, okay? So if you think of it as a mathematical function, you got this sort of recursively callable function where you'd call f with some f0. The first s0 is known as the random seed, okay? And so if you know what f is and you know what f0 is, you can figure out s1. From that, you can figure out s2, and from that, you figure out s3. And so the entire sequence of random numbers, so if I type, again, this entire sequence of random numbers is determined in advance just by knowing this state, okay? So, and this is literally how it works in Julia. There's actually a kind of, do I talk about this a little bit? Yeah, there's a kind of internal object here. I think it's called default. RNG, something like that. And you can get this random number generator. And I think I can kind of dump it out. We can kind of see what's in it. Oh no, it doesn't. Anyway, we'll probably get to that in just a second. Well, we'll have a poke inside it and we'll tell you what it is, okay? So this function f, like as I said, there's some state, but it's also a function. Now, it could be any function, right? It could be like x goes to x plus 1 or something. But this wouldn't necessarily be random, right? It'd be very easy to predict the next value of x, and it wouldn't be very useful for doing Monte Carlo simulation. So we want a function which is deterministic, but it needs to be sort of complex in a special way. Something like a hash function if you've done some computer science. Some properties we might want to hold is like if you have elements xi and xj, from the sequence, they should just basically appear independent. You can't really like predict one from the other. So if you know, say, x1, you shouldn't be able to figure out what x2 is. The distribution of xn should appear kind of random, right? Sorry, uniform. Or if you're trying to generate, say, bits, random bits on a computer, like 32 random bits or something, you should be filling that sort of space uniformly. And so generally, you shouldn't expect some elements to turn up much more often than others, right? The range covered by xn should be sort of known in advance, well defined, right? It's a 32-bit one or it's a 64-bit one or something like that. And if it's a sequence, right, what's going to happen is if you have, say, n bits, there's only 2 to the n possible values, right? So if you imagine the sequence, if you go through all of them after 2 to the n, you'd probably come back where you start, come back to where you started, and you have another cycle. Okay. Now, to be clear, that cycle length is actually determined by the number of hidden bits. Okay. So like the random number generator in Julia I was trying to show you there, it has like 256 sort of internal bits of hidden state. Okay. Yeah, but you could also imagine a more primitive kind of random number generator, and it might repeat. You might have 0 goes to 1 and 1 goes to 0, and that'd be like a short cycle. So you want those cycles to be long. And for cryptographic applications, like I was saying, if you want to make up a secret password, if your bank app talks to your phone or something, they use, kind of cryptographically secure random number generators, where basically from the outputs, the x's, let's say I don't just have one x, I got like 10 of them or 100 of them or 1,000 of the x's. It should be basically computationally feasible for me to figure out what state you had. You can always do this by brute force. You could always try state equals 1 and see whether it's the sequence, or state equals 2 and try to see if that's the sequence. But for cryptographically secure sort of hash functions, you wouldn't be able to go backwards. The best thing you could basically do is just this brute force attack. And so long as you have enough bits in your hidden state, then it's basically impossible for someone to guess your hidden state. Yeah. So typically we're generating sort of random bits, maybe like 32 bits or something. So how would we do something like create a floating point number? Well, if you just divided it by, say, you had L0 from the range 0, elements 0 to 2 to the L minus 1, if you just divided by 2 to L, right, you'd get some number between 0 and 1. It wouldn't include 1. It'd sort of be a range which is closed at 0 and open at 1. And that would be fine. But division of integers is notoriously slow on CPUs, and we're going to generate lots and lots and lots of random numbers. So what we actually typically do, say in Julia, is create 52 random bits and just fill in part of that floating point number. So if you cast your way back, you mind back to the first part of the course with Paul Billette, and we're talking about the mantisses and the exponents of the floating point numbers, we can come up with a scheme where we can uniformly sample between the number 1 and 2 by setting the exponent to 0 and filling in the significand or the mantissa with just some random bits. Okay. So if we do that, you'll end up with some number that starts with 1 and is less than 2. And then if we subtract 1 from that, we'll get from the range 0 to 1. And if you actually dig into the guts of Julia, there's actually, and they do it for a few function calls, but if you put it together, they actually do this algorithm here. Okay. Does anyone have any idea what this 0x3ff thing is all about? Any guesses? Yeah, the back here. Kind of. So what we're doing is we're taking So there's uint 32, and that's going to fill in these bits here. Okay. But if you cast your mind back to your floating point numbers, you got some things going on. You've got like a sign bit and stuff happening here at the top. But for the float 64s, you got these exponents that can be between like minus 1024 and positive 1023 or something like this, right? So this thing represents the number 1023. Okay, and so that basically is setting that exponent to 0 for you. Okay, that's why it's that. Cool. So we basically construct these 52 random bits, and this thing is basically taking a 64-bit number and truncating the first 12 bits away. And then, yeah, that's that. So yeah, the one thing that we're doing in Julia when you call rand is that this thing is actually short for calling it this way, like that. And it's actually sort of possible for us to provide our own random number generator. And we'll talk about that in just a few paragraphs. So I think I talked about this before. You might want to know where the sequence starts, and this is usually done by specifying the seed. And for a lot of different reasons, you might be interested in initializing your random number generator with the seed. So for example, if you're debugging a program and every time you run it, it comes up with different random error, it's going to be very hard to figure out what's going wrong. But if you can rerun it with the same random set of random numbers, you'll be able to like fiddle with the program, figure out what's going on, right? It'd be very hard to kind of understand what's going on in your program if it's every time you do something, it does something different. And there's good statistical reasons with where you can do variance reduction techniques, why you'd want to like share and reuse a random seed, and we're going to talk about that. Yeah. And obviously, if you're doing a scientific paper or something, you might want to be able to regenerate your results exactly to the point where you might specify the seed in your academic paper or with accompanying code or something like that. So let's have a look what's inside a pseudo random number generator. So one thing that it's not, these things are deterministic. They're not non-deterministic. So if we just create some take an array of Julia and tell it to use some undefined RAM, if I just type this in here, I'm going to get some kind of bits or bytes on my computer that have been in my RAM. They're bytes that have been used before by some other program or maybe by Julia before it sort of reallocated this RAM to this array. Okay. And possibly if I run it again, I get something different. If you just turned your computer on, it's more likely maybe these are all just zeros, for example. So this isn't really what I'd call like suitable for a random number generator. It's not even sort of well defined what you're going to get out of this. If I use a different computer, I might get, always get 0 or something. It won't be random at all. So it's sort of arbitrary, but it's not what we're after. So the way we often work about this is we use sort of number theory. Okay, so number theory has a lot of results about all these cycle lengths and groups and all these sorts of stuff that we can leverage to create a good random number generator. So the simplest class that you probably come across is something called a linear congruential generator, or LCG. These are very sort of famous, very classic algorithms, but 100% outdated today. I wouldn't recommend using them in a production system. But they're simple enough that we can just talk about it for a minute. You can sort of learn how it works. Okay. So if you're like me and you grew up with computers in the 80s, this particular algorithm is probably the one it was using. What it is it's literally a linear transformation, or technically an affine transformation, where you sort of take And another thing that makes it really simple is the state and X exactly the same thing, right? X is the state. So you take your previous result and you multiply it by some constant, and then you add a constant, and then you take it by a modulo. Now, it's okay if all these things are kind of co-prime. And so it's perfectly okay for the modulo to be some power of 2, so long as A and C don't have factors of 2. This is very convenient for computers where you might have like 32-bit or 64-bit registers, and that's what you want to use, okay? So addition and multiplication for unsigned integers on your CPU will automatically wrap around and do modular arithmetic for you, okay? So you get that really cheap for free. So generally we'd set this thing to be like 2 to the power of 32, right? So 32 bits, unsigned integers. And we got to just find some values for A and C. You get good cycle length so long as everything is coprime, I believe. No, that might be wrong, but I don't know. I think that's right. But you can sort of search around for parameters that work well. So here's a really sort of famous or classic example where A equals this number and C equals 1. And it provides reasonable performance, right? And I'll show you the results just here. But you know, back in the 70s and that, you could buy, you know, paper textbooks and stuff, and they would have tables of different numbers to suggest to try, and you'd go and type them into your Fortran program and write your own random number generator that way. Okay, so let's have a look at this. We're going to create some plots here, and we're gonna create this algorithm. So this next function, this is our F, our random number generating function, okay? It's a function of the previous value Z. We're going to create a million different results. We're going to start with a seed of 808, okay? And we're just going to like populate this data vector with these results, okay? And we are doing this slow division thing here. This is more for demonstrative purposes than anything, to get some number between 0 and 1, and we'll just plot them. So if we do a scatter plot as a function of n, we don't really see any special correlation with n. It looks kind of random, which is good. It looks good here, has sort of voids and dense bits, which is actually what you expect for random numbers. They do kind of bunch up a bit. And if we sort of take little slices, horizontal slices, and kind of integrate them, we can turn it on the side. We kind of get this plot here, which sort of tells you, you know, what's the probability of the number between 0 and 0.01 or something. That's what each of these bars are, and you can see that's relatively uniform. So it's actually pretty good at generating uniform numbers between 0 and 1 that appear relatively uncorrelated. So it's not so bad. But it is pretty easy to break and hack. It also has enough pattern in it that that pattern, if you use this in a real simulation or something, that pattern will actually be visible in all the results and everything. So it's not by no means a perfect random number generator. Okay, so but it's okay. It also has you know, a full cycle, so you know, we'll go 2 to 32 times. So in Julia, Julia will actually have an algorithm and keep this hidden state for you. It's very clever. It has, for every thread or sort of task that you make in Julia, it will have its own random number generator state. So when you do multi-threaded programming, it doesn't all clash and get confused. And that's what that default RNG, this thing that I had before, this task local RNG. So RNG is random number generator, just in case it wasn't clear. So that's sort of the default one. Now, what that thing is internally is actually one of these, this thing, sure. Yeah, it's one of these things. Yeah. But it's hidden away and it's attached to the thread, the task. So what we have here is actually, it consists of 4 uint 64s. Okay, so it's basically 256 bits of kind of state inside of it. And let's say I can sort of construct one, and I can use it to then I can call, say, rand with that thing, which is all fine. Okay. And once I've done that, the internal state of that random number generator, you can see in this top bit and this bottom bit, it's actually changed. It's been mutated. Okay. So this object is a mutable struct in Julia, right? It gets modified over time. It's not just a simple value. Now, if we specify a seed, it can kind of like take, say, a 64-bit number and sort of hash it and make 256 bits for us. It's usually easier just to give it like a little integer to initialize it. Easier to remember as a human. But that's deterministic. And if we kind of like run it twice, before and after, we get the same kind of numbers. So like we can use this random number generator to create an integer and then a complex floating 64 number. We get those two results. And if we do it all over again, we get those two results. So that's how you kind of, in Julia, you would create, you create this random number generator and then you'd use it here. Now that's all optional, right? Putting it in there. So you just want to do that for your, your projects and your stuff where it's important that you can kind of do it deterministically. But if you're just playing around with REPL, you wouldn't bother about this stuff. You just sort of like YOLO it. Right. So one of the good reasons why you'd want to do this also is that is this sort of variance reduction techniques I was talking about. So let's say you had some simulation, some process which is occurring, and it has a lot of noise. Okay, and you're trying to look, for example, one thing you often want to do is, oh, what happens to how sensitive is my simulation to some parameter? So in this case, the parameter is alpha. How much does the result change if I change it alpha a little bit? Maybe I want to take even a derivative or a numerical derivative with respect to alpha of the result. Okay. Well, we're going to do two kind of things here. We're going to create this path, which is a drunken walk, and we're going to run it with the same random number generator each time and with different random number generator each time. So this is a drunken walk, a random walk in 2 dimensions. We start with these parameters x and y, which are sort of real numbers. And we sort of have 4 possibilities here. Every time we flip a 4-sided coin, I don't know why it's called flip. And we either move up, down, left, or right, depending on the result. And that's sort of a random diffusive kind of walk, a bit like Brownian motion. Okay. And we've got this bias with alpha, which means we go up and to the right a little bit, depending on alpha, or if it's negative, we'd go down to the left. And we're going to do like 5,000 iterations of this and plot it. Okay. So in this first one, we use all the same random numbers, and the second one I'm using completely different ones. And what you can see is if I'm using different random number generators, I don't see much of a pattern. But here, if I'm just evolving alpha slightly, increasing it from 0 to some other small numbers, what we can see is the simulation is slowly drifting up and to the right, which is what we said. Alpha was a drift term that moved it up and to the right, okay? So that's all fine. And, I could even take the limit and find a derivative or something here. Now, if I was interested in the same thing here, well, the variance or the difference between these trajectories just dominates. If I was to ask you what does changing alpha do, you might come up with some magical story like, oh, well, every time you increase alpha, you rotate the picture by 120 degrees and you do something. You can't really determine what the pattern is. So one way to get around that is you run a trillion trajectories, like 1 million or 1 billion or 1 trillion trajectories here, and to get that variance down, so that you could see the effects of different alphas. Or you could have just chosen the same seed and compared correlated results in the beginning. And that, even with this is a linear problem, so even with a single trajectory, you're getting the right result. Yeah. So those kind of variance reduction techniques are very powerful. Now I'd like to spend the rest of the lecture. I've gone a lot slower than I should have. Talking about how to go from certain distributions to others. Okay, so we got this uniform distribution between 0 and 1. That's all down pat. And we could probably pretty obviously transform that. We could do like a linear transformation to go between some interval between A and B. We could do a Bernoulli distribution, like if the number's less than half, it's heads. If the number's greater than half, it's tails. Those kind of distributions, right? And in fact, if we have maybe some finite number of states or whatever that we want to predict, so like in Julia, I can go like rand, and then I can go like set. I can pick. I can do this sort of thing in Julia, right? So how does this kind of thing work? So this will kind of like give me different elements of the set. So we can put in the probabilities for all these things, okay? And then we're interested in the cumulative distribution function for that, okay? So what cum sum does is the first one is just the first one. The second one is the sum of the first and the second one. The third one is the sum of all first three, and the fourth one is the sum of all four, okay? And if P was probability distribution, well, this thing's monotonic and starts at 0 and goes up to 1, okay? So, and we could draw the distribution, we could plot it. But if we can go from if we know the CDF, what we can do is make a random number between 0 and 1 and kind of see where we land. If we get 0.7, well, we're going to be somewhere in the interval here between those two numbers, between 0.6 and 1. And so we can say in that case, we're inside this sort of chunk of probability, okay? I should probably have another plot here where I can actually do this a bit more visually. But you can basically project some random number between 0 and 1, which is your probability or your cumulative probability, and project that onto one of these elements, okay? And that projection is exactly like a functional inverse. So we have a function from the probabilities between 0 and 1, or that interval, to these, or what do I say? What is it? The CDF. I'm just trying to get this right. So this is a function, right? Yeah. So this is the inverse. So given a random number, it's pretty easy to figure out which bucket it's in, which is fine. Okay. So yeah, so if you do know the cumulative distribution and its inverse, it's quite powerful. You can kind of do whatever you want. So let's look at some more. Let's look at the Bernoulli distribution. The way you'd probably attack this, or one way you could attack this, is literally like run it like a series of experiments. So just remember the Bernoulli distributions when you like flip a coin n times, right? And so what sort of distribution do you get? But that obviously will get slower and slower as n increases, right? So you could probably do this a little bit more directly if you're a little bit clever. For example, you know things about this distribution. You sort of know the mean is the probability of getting the result you want times the number of times you try. Okay, that would be the mean probability of getting the sort of affirmative result. And you can calculate the standard deviation, which, because it's a binomial distribution, it's not too hard to calculate that. And so, let's say we had n equals 20 and probability 30%. We could figure out the mean standard deviation and get numbers like that. The mean is 6, 20 times 0.3. And if we did like 1 million Monte Carlo samples, we could use this function, which again was slightly slow, but it's fine. We could do that a million times, and we can kind of see what we get is a mean very close to 6 and a standard deviation very close to the result up here. Okay, so it's kind of cool. So this is sort of, there's your introduction to Monte Carlo right there. Julia has this great package called distributions. Like I just encourage you to, like, you do things like you go like using distributions, right? And it sort of tells me, oh, I don't have distributions, you want to install it. So I just press yes. That's fine. Okay, so it's very easy to get up and running. You can explore and experiment with these things. Oh, it exploded. I didn't expect that. Okay, I've pinned my data structures. We can fix that, but I've spelled it wrong, haven't I? We'll see. We'll come back to that. I was just trying to show you how easy and flawless it works. But anyway, exponential distribution. This one's a great one. Okay, so if often you'll come across things and people have this magical way of calculating some random number. So exponentials one, where this is like this sort of like half-life kind of distribution, decaying probability function. So you have this rate lambda, which is sort of like the inverse of the half-life, and you have this probability distribution function which decays exponentially with some x. So half-life, that'd be like time versus the chance the atom hasn't decayed yet, or something like that. So for different values of lambda, as lambda gets larger, the rate gets faster, and the function gets more and more squashed over it towards the origin. Eventually, it'll approach something like a delta function of 0. So it turns out you can just sort of use this function, and that would tell you, that would give you a random estimate of that function. Now, how does this work? Okay, so one thing to realize about these three functions is if I change lambda, these functions are just sort of stretched out. Now they have to stay normalized because they're probability distribution, so they also get up higher and lower this way. But if you change lambda, they just stretch out this way. Okay, so that relatively easily explains this fact that you got some random function divided by lambda, right? But the fact that this is a log is maybe a bit surprising at first. I did give you a hint before that we're going to invert some cumulative distribution functions. So if we invert an exponential, we get a log. Okay, but this works out quite neatly here. Okay, so let's have a little look here. If we have a random variable x, the CDF x is the function where it's the integral. It's the integral of the probability less than x, right? So it starts at 0 and goes to 1 eventually. So if we integrate a decaying exponential, we get 1 minus x lambda z, because there was a lambda there, which sort of gets cancelled out, and so that varies between 0 and 1, and it sort of has this kind of shape here, like these ones. Okay, and these ones are literally stretched out by lambda, so there's not even any scaling function here; they're just stretched. Now, if I want to take the inverse of that, well, we've got this funny 1 minus thing happening here, and we end up with this 1 minus there. But we have this really cool insight, is that if we're drawing p from the interval 0 to 1 randomly, uniformly, then 1 minus p is exactly the same distribution, right? You're just mapping 1 to 0, 0.5 stays at 0.5, and you're just sort of taking the mirror image of a sort of top hat kind of distribution. And so you could actually just replace that with some other kind of random number, which is equal to 1 minus p. Okay, so pretty much you can take minus log of some random number and divide by lambda, and you get the thing. That's great. I'll just do the Gaussian, and we'll finish up next week. Okay. So the Gaussian's really sweet. It has this very intuitive thing that you could probably have guessed without me even telling you. It looks like this. It's called the Box-Miller transform. Okay. So this thing's a bit wilder, right? Like I told you, the log is the inverse of an exponential, so it's probably not too crazy. But what's going on here? It's got a cosine, right? Another weird thing here is you can replace cosine by sine and you get exactly the same result. But yeah, let's see what's going on. This term's maybe, if we're talking about inverting a Gaussian, it might not be too crazy. There's a log there, there's a square root, a factor of 2 from the power of 2. You know, you can imagine doing some calculus and ending up with something like that. So let's see how that works. Now, who remembers integrating a Gaussian? I remember when I first learned the power, the joy of integrating a Gaussian with this trick. The trick is you got to do it in 2D, not in 1D. Okay, so you take two Gaussians in 2D, right, and multiply them by each other. You end up with this circularly symmetric, rotationally symmetric distribution. Okay, and so that's what this squared thing is, right? It's sort of like a Gaussian x times a Gaussian y, but we don't care if x and y are the same sort of symbol here. Oh, here they are. There they are. All right. So we square it. We get this thing. Then we turn that into polar coordinates. Right. So we transform x squared plus y squared to r squared. Right. And what else do we do? Because we used integration by parts or whatever, we've ended up with this r here. Oh no, that's right. That's right. Dx dy is equal to 2 pi r d theta dr. That's what that is, right? That's fine. And we're integrating the theta part from 0 to 2 pi, which is just the factor 2 pi. And this one is easy to integrate by substitution. It's just, if we substitute for capital R, you know, such that dr is r dr, we get this integral here. This integral is simply results in 1. Okay. So the answer is 2 pi. And then we can, that's how we do that integral, right? And so, where are we? So we are going to do sampling. We want to do sampling of a distribution like this one here, right? Let's have a look. So rather than drawing an x and y on the circularly symmetric thing, we're going to generate a random r and a random theta, okay? And use the relation that x is r cos theta and y is r sine theta. And we're going to take advantage of that rotational invariance such that that theta is just some random number between 0 and 2 pi, right? That's fine. So now what we're going to do is figure out r, right? So rather than drawing r from this distribution, we can draw a capital R from that distribution, right? This is exactly the same transformation we apply from here to there, the same integration by substitution, whatever it is. And we would get the same kind of result, so long as we remember to transform R back when we're done. Okay, so if we're going to use this transformation I mentioned here, right? So once we're here, we can use our old friend that we saw before, the logarithm one. Okay, so we can draw a sample for R using minus log of rand. Okay, and then we can go from capital R to little r by using this transformation, right? By you know, R is that thing. So because sorry, big R was half R squared. So little r is square root of 2 big R, right? And so we just substitute that log thing in there, we get this. Okay, so now we've got our R, we've got our theta, and we can put this function in like this, copy it in, and we can do the Monte Carlo thing again. We can just create some grid that we want to plot. So we create a bunch of random numbers, a million of them to be precise. We bin them up into a histogram of 50 bins, and we plot that against the actual Gaussian distribution, and you can see how well it fits. Okay, so if I did finer grained bins and more Monte Carlo samples, it sort of does fit perfectly. So it's a pretty neat trick. Okay. I will at beginning next lecture talk about recap that and talk about these other ones. There's two other very important techniques here that you can use, and finally we'll discuss our discrete event simulator, which is fun. So we'll have 5 minutes of this, and then action time for project 2 and all that content. Yeah, thank you for listening. We'll see you next week. And yeah, don't forget we're around for the Thursday evenings with Yoni and me. Take advantage of your pracs. Get more.